In this video series, we'll be showing how to optimize your night tower configuration to meet your PPA requirements. We'll consider this reference design and perform various optimizations on it in the upcoming videos. Through this series, we'll be covering key NI tower concepts and sharing recommended practices that will be useful while configuring the NOC. It is recommended to go through the NI tower creation flow videos on YouTube if you're not already familiar with the interconnect architect. In this video, we'll understand this reference configuration, go through the area report, and run the performance model on the reference configuration. Let's take a quick look at the specified domains, global parameters, interfaces, and the memory map on the interconnect architect. Under the Domains tab, we have one voltage domain, two power domains, and three clock domains in total. In the clock domain relation editor, the crossing type is configured to be asynchronous between all the three clocks. In the Global Configurations tab, all the parameters are set to the default values. For more information on what these parameters are, please refer to the NI tower creation flow videos. In the Interfaces tab, we see 4 completer and 5 requester interfaces. Under the Paths tab, the Path Matrix editor specifies the path between the requester and completer interfaces. Within PP optimization, the parameters on the general pane are set to the default values, and the traffic and timing parameters are not used in this configuration. The next page is memory maps. We see one default memory map that all the 4 completer interfaces subscribe to. Moving on to the Canvas tab, here all the IP blocks were placed onto the floor plan and the corresponding interfaces were associated to the blocks. After placing all the HLS floor plan elements, NOC-SC was used to auto-generate the microarchitecture. As you can see, in the NOC-SC generator topology, all the links are configured to be low wire. This is because we did not provide the synthesis engine with any information about the traffic requirements. A low-wire link will have only 2 channels, a request channel and a response channel. Since all the links are low-wire, we can expect a low area count but also limited performance as it won't be able to support simultaneous reads and writes on a link. The area report can be generated by executing the report area Python script under the Test and Report tab. The total area for this reference design is 36,034. Or 36034. We will now inspect the performance of this configuration by running a traffic case using the performance model. We have defined separate read and write profiles for AXI and ACE, and these are further grouped into 2 traffic groups, one for AXI and one for ACE. The injection rate is set to 3000 picoseconds for reads and 4000 picoseconds for writes. Clicking on Results under the Test Cases tab after running a traffic case dumps out the results as a set of statistics. The Result Context tab provides a graphical view of the test results. The write bandwidth on the ASNIs are 1778 megabytes per second, 889 megabytes per second, and 889 megabytes per second respectively. This is roughly around 14 gigabits per second, 7 gigabits per second, and 7 gigabits per second respectively. The read bandwidth is also the same. In the upcoming videos, we'll see how to optimize this reference configuration to meet your PPA requirements.